Well, first we'll look at a couple of theorems that we've already made references to indirectly in previous videos, and then we'll do a couple of mathematical induction proofs. The first theorem, GWO, we've seen WO, the well-ordering property. This is the generalized well-ordering or well-ordered property. It says that if m is any integer, positive, negative, 0, then this set is well-ordered. Well, we already knew that the natural numbers are well-ordered. And all this is saying, another way of writing this S, let's just say m equals -5. That implies the set S would be -5, -4, -3, -2, -1, 0, 1, 2, 3, ... And that kind of makes sense. Clearly, every subset of this has a minimum element. And that leads us into this generalized well-ordering, leads us into what I just put in like the name GMI. MI is mathematical induction, which you've been learning about. And this is a generalized mathematical induction. The theorem we looked at before said that if a statement is true, if you have propositions or statements, P1, P2, P3, ... The mathematical induction said if P1 is true, and you can show then that PK implies PK plus 1, in other words, PK being true implies that PK plus 1 is also true for all K, then that propositions are true for all natural numbers. That means P1 is true, P2 is true, P3, ... they're all true. Well, this one says Pn is now a statement for all integers with n greater than or equal to m. So now this could start in the negatives, or it could start at 10, 5, -8. Okay, that's the statements. If Pm, which would be the smallest one, is true, and just like before, Pk implies Pk plus 1, and again, that means Pk being true implies that the next one, Pk plus 1, is true for all k that are greater than or equal to m, then Pn is true for all of those statements we defined, for n being greater than or equal to m. So, just as an example, m equal, I'll use -3 this time. If m is -3, that means our statements are P -3, P -2, and so on to infinity. So what this general mathematical induction says is you prove this one true, and then, just like before, you prove this. You pick an arbitrary k and show that Pk being true implies that the next one, Pk plus 1, is true. And then overall, this would show that P -3, P -2, P -1, ... toward infinity would all be true. So simply generalized, two generalized statements of previous statements we looked at were a little bit more specific. All right, one definition, and then we're going to do a couple of induction proofs. Excuse me. First, the definition. We say in factorial, but we write in with an exclamation point. In with the exclamation point means n is some positive integer. Well, I guess it could be 0 as well. And in factorial is n times n minus 1 times n minus 2 all the way down to 1. So another way of saying that would be when n is a non-negative integer, in factorial is the product of the first n positive integers. And then this is really, maybe I should put a colon in front of the equals like it's a computer statement. This doesn't make sense when you see it. 0 factorial is equal to 1, but that makes everything work. So this is a definition. We're just defining 0 factorial to be the number 1. So just some examples. We know 0 factorial is 1. 1 factorial is also 1. 2 factorial is 2 times 1. And I'll do one more. 5 factorial is 5 times 4 times 3 times 2 times 1. And just to review a little bit here, why that's true. 1 factorial is 1. If n is a 1, well, we're starting at 1, and we're going all the way down to 1, which means really, this is a little bit misleading. There aren't 1, 2, 3, 4, 5, 6 different terms, products, or factors, I should say, that would just squeeze into one number, just the number 1. Oh, and let's do a quick property. Notice, this is just an example. Notice that 10 factorial is equal to 10 times 9 factorial. Sometimes that comes in handy. 10 is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, all multiplied together. 9 factorial is 9, 8, 7, 6, 5, 4, 3, 2, 1, all multiplied together. And we let off with a 10, so those two things would be equal. And one other example would be if you had 10 factorial over, say, 7 factorial. If you write out 10 factorial, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, all multiplied together as the numerator, and you have on the bottom 7 times 6 times 5 all the way down to 1, well, the 7 down to 1 are going to cancel out. Another way of saying that, I could write it like this. 10 times 9 times 8 times 7 factorial. That's another, the numerator, that's just another way of writing 10 factorial. 10, 9, 8 multiplied together times 7 factorial, because the 7 factorial takes you all the way down to 1. And now you can see the 7 factorials cancel, and we just get 10 times 9 times 8, which I think is 720. So working with factorials in fractions, very nice the way they cancel. 100 factorial over 99 factorial, it's 100. Okay, we're ready for an induction proof. Prove this statement holds for n greater than or equal to 4. And let's just see, assuming this is true, let's see if the n equals greater than or equal to 4 is the best case possible. Let's see if it would also work for 3. 2 to the third would be 8. N equals 3. 2 to the third would be 8. What's 3 factorial? 3 times 2 times 1 is 6. And indeed, it fails. So assuming this is a true statement, which it is, n greater than or equal to 4 is the best possible number you could use. It's the lowest possible number that guarantees success for n equal 4, n equal 5, ... All right, so what we will do is, let's do the base case. I'm going to erase this. I'm going to do the base case over here just so I don't run out of room. I don't need to write base case. I'm just going to write n equal 4. Proof. N equals 4 is going to be the base case. All right, 2 to the 4 less than, I'm going to put a question mark above it because I'm not sure yet, 4 factorial. Well, what does that mean? 2 to the 4th is 2, 4, 8, 16. 4 factorial is 4, 3, 2. I don't even have to write the 1 in the factorial, but I do. I did. 4 times 3 is 12, times 2 is 24. Check. It works. So the base case worked. So now we need to do the inductive hypothesis step. So basically we could say, suppose 2 to the k is less than k factorial for some k greater than or equal to 4. So we're assuming that this is true for k. To prove that the statement holds for k plus 1, which means the The left side would be 2 to the k plus 1. And the right-hand side would be k plus 1 factorial. So we've now explained to the reader exactly what we're going to do in this inductive step. And as soon as we do that, we'll be done with the proof. All right, well, we need to prove this. We're assuming this is true for some k to prove that that's true. So let's just start off by notice, or some word like that. 2 to the k plus 1. I'm not ready to go there yet. But what is 2 to the k plus 1 equal to? I need to make it look like this. I need a 2k out of that. So I'm going to say it's equal to 2 times 2 to the k. And I'm going to write that in a different color. You'll see why in a second. And what can I say that's less than using the inductive hypothesis? Well, 2 is just equal to 2. But 2k is less than k factorial. So that statement I can make in red. I just rewrote this. 2k is less than k factorial. So if that's true, if you multiply both sides by 2, the inequality is going to hold. If you multiply by a negative number, it would reverse it, but we're not. We multiplied it by 2. Okay, so I think we can just go ahead and conclude this statement. Maybe I'll do this in 2 steps. Underline that too. Maybe I should have used a different color. Yeah, I got my pattern of colors off now. But this should be obvious. It's an inequality, it's a less than. We have a k factorial and a k factorial. But we've got bigger because I had a 2 here and I replaced it with a k plus 1. And k is at least 4, so clearly that inequality holds. But this is equal to k plus 1 factorial, and we are done. We proved that 2 to the k plus 1 is strictly less than, because we have a strictly less than along this path, k plus 1 factorial, so this is exactly what we have proven. So that one was nice, basically a one-line proof, if we ignore just this explanation of what we were going to do. Okay, let's look now at the next one. Prove that 3 divides this number. Oops, this would be for all. Yeah, I'm going to keep it in. For every natural number n, 3 divides 4 raised to the n minus 1. So let's just start off, see if I can get the base case on this line. I'm just going to write what the base case is. It's the n equals 1. Okay, does 3 divide 4 to the 1 minus 1? Yes, that's obvious. I'm not even going to put a question mark there. 4 to the 1 minus 1 is 3. 3 goes evenly into 3. So the base case, I'll go ahead and say 3 divides 3. We're done. Now we're going to jump into the k. I'll use a k, and maybe I'll do the explanation again. Suppose 3 divides 4 to the k minus 1 for some k in the natural numbers. That's what we're going to assume is true to prove the next one, the k plus 1 case. The k plus 1 would be, well, there's k only shows up one time. Just replace k with k plus 1. 3 divides 4 to the k plus 1 minus 1. Now I'm going to state a kind of a mathematical fact before we dive into the proving the inductive step. Let's first realize what this means using the definition. I'm allowed to say, since we're assuming 3 divides that, I can say let r be an integer. Let r be such that 3r equals 4 to the k minus 1. And if I wanted to put the explanation in there, I would say that's just the definition of what it means to divide. If this divides that, that means this is a multiple of the left-hand side. It means there's some integer I can take 3 and multiply it by to get this. All right, now that we've made that clear, now we're going to try to find a number, integer, that I can multiply 3 by to get that. So let's see if I can get this done in one line. Let's see. What is 4 to the k plus 1 minus 1 equal to? Let's say, but 4 to the k plus 1 minus 1. Remember, if we can get this equaling 3 times an integer, we're done. And what would that be equal to? Well, I could break the 4k plus 1, 4 to the k plus 1 into 4 to the k. Maybe I'll write it like 4 times 4 to the k. 4 times 4 to the k minus 1. So, I mean, I just factored a 4 out. If you take the 4 to the 1, 4 times 4 to the k, you get 4 to the k plus 1. But we know exactly what, let's see, what do we know? We know 3r is 4 to the k minus 1. So, how could we do a substitution here? What do we know from this right here? What is 4 to the k equal to? If I add 1 to both sides, I get, I'm just going to replace that 4k, and I'll do it in red in a minute. That's going to be 4 times 3r plus 1 minus 1. So what I did, the part I'm going to do in red, is I'm going to write that in red, just to make it very clear here. 4 to the k is equal to 3r plus 1. That is from the inductive hypothesis, which is this. Okay, so what is that equal to? What is that simplified to? 12r plus 4 minus 1. 12r plus 4 minus 1 is 12r plus 3. 3 goes into that. Equals 3 times 4r plus 1. And we're done. We just proved that 4 to the k plus 1 minus 1 is equal to 3 times a number. Maybe if I have room at the bottom, I'll just say, and 3 divides 4 to the k plus 1 minus 1. Once again, that's because 4 to the k plus 1 minus 1 is equal to this. So obviously 3 divides that. And that's the end of the proof.